Good afternoon, everyone. So as my title implies, I'm going to be talking about imagery products, specifically for fire detection and monitoring. And I do think there's a lot of value to the imagery. So when I first tried to publish a paper on this, I was told by an anonymous reviewer that you cannot use images to detect fires. And I thought that was very short-sighted because we know that the National Weather Service is using imagery to detect fires on a daily basis. The other thing that anonymous reviewer told me was that the essential component of a fire detection algorithm is identifying the latitudes and longitudes of the pixels that contain fire. But imagine if you are a fire manager on the scene of a raging wildfire and someone hands you a piece of paper, or in this digital age, a text file that just has a list of latitudes and longitudes in it. Is that going to be very useful to you? At the very least, you're going to want to plot those points on a map. But the satellite actually offers a lot more information than just plotting hot points on a map. And I think that's where the imagery can come in. So I refer to this RGB as the natural Fire Color RGB. And what you can see is not only the hot spots where the fire is most active, but you can also see the burn scar and get an estimate of the fire perimeter. You can see the clouds and the smoke here. You can see rivers and lakes in this imagery that would act as a natural boundary for fire growth. And you can even see differences in the green coloration of vegetation, which are going to impact how the fire burns, if it's burning in a wooded area versus a grassland area. And so all of this is information that you can't get from a straight level 2 fire product. And of course, I'm also going to talk about the Fire Temperature RGB, which relates the intensity of the fire to color. So satellite imagery really is a synergy between art and science, and it's very subjective. Here are 6 different ways of trying to discriminate snow and ice from clouds, for example. And whichever product you use is going to be the one that catches your eye. But I do think there are some guiding principles that we can use when developing new imagery products. And the first is you want to maximize the amount of information that's present. And so I lifted this image from an old US Forest Service website many years ago when they first learned that you could use the VIIRS day-night band to detect fires at night. And they wanted to distribute this imagery to their user base. But when I looked at this image, I found it very hard to identify where are the fires in this image. And I'm supposedly an expert on this. What does the average person do with this image? So I grabbed the data and I played around with it myself. And I'm pretty sure that they just scaled the raw radiance values from the day-night band between the maximum and minimum in the scene to create this image. But if you use a more intelligent scaling with the same data, now you've brought out a lot more information from this image. Now you can see where the clouds are. You can see where fog is encroaching in these coastal valleys. You can get a sense that there's some smoke in the atmosphere up here, and it's easier to distinguish these fires from the city lights. Another thing that we should inspire to is making things intuitive. We want them to be easy to interpret. And so here are 2 different examples that were tweeted by the National Weather Service. So the image on the left uses the color table for the 3.9 micron channel alone. And you can compare that with the Fire Temperature RGB. And since this image was shared on social media, I always wonder how many members of the general public can tell where the fire is, that it's this black blob and not any of the red areas surrounding it. Whereas the fire temperature RGB, it makes fires look like fires. And I think that's one of the advantages to it. So, I mean, this was already covered in the talk this morning by Yvonne, but the basis of it is that the 3.9 micron channel is sensitive to a wide range of fire sizes and intensities. But as you go to shorter wavelengths, fires have to be proportionally more intense in order to be detected, because we're getting more radiation from the sun, and the surface is becoming more reflective as well. So the 2.2 micron band is really only sensitive to moderate intensity fires and above. And when you get to the 1.6 micron band, that's really only sensitive to very intense fires. So when you combine them in this RGB, now you have, a fire where cooler or less intense fires will show up as red, and then as they heat up, they'll become orange to yellow or white hot once they're visible in all three channels. But you can detect more than just fire intensity with this imagery. And so here's a case from earlier this year where you can actually see this cold front pushing down from the north that impacts this fire in the Oklahoma Panhandle. So you can see a fire gets started here, and the winds are initially pushing it off to the east. Then the front crosses, and the fire rapidly changes its direction. And knowing that the front is going to arrive is important for firefighters on the scene who need to be able to get out of harm's way before the fire changes its behavior. And I also want to make the point that resolution and perspective matter. So this is a fire that happened in northern Alberta in Canada a couple of years ago that was visible from both GOES. So GOES 16 to the east, GOES 17 to the west, and from two different VIIRS instruments. And natively on VIIRS, these channels have 750 meter resolution as compared to the 2 kilometer resolution from ABI. But since this fire was far enough north, the resolution is even degraded from the 2 kilometers at the equator. And you can see that you get a lot more information about this fire from the higher resolution VIIRS images than you can from either ABI, including this spot up on the northern end that's a lot more intense that you really can't tell from either ABI. But what we've heard from fire managers over the years is that even 750 meter resolution isn't quite good enough for their purposes. And so that led us to develop a 375 meter version of the fire temperature RGB for VIIRS, which we can do because VIIRS has high resolution 1.6 and 3.7 micron bands. And then we use variance encoding to downscale the 2.25 micron band to 375 meter resolution. And so here's the original 750 meter version compared with the 375 meter downscaled version. And notice that there are some hotspots down here that show up with the high resolution version that don't show up very well at 750 meters. And we can validate this by comparing against the natural Fire Color RGB, which is available natively at 375 meter resolution from VIIRS. And so some more background on this RGB. I know it has gone by many different names by many different groups. And so the National Weather Service refers to it as the Land Cloud Fire RGB. And a lot of fire managers, they like to just call it the Fire RGB. But the basic idea here is that the visible channel is your blue component, the vegetation sensitive channel is your green component, and the 3.9 micron band is your red component. So now the hotspots from fires will show up in red. The vegetation band will give you information on vegetation health and the burn scars. And the visible band will give you information on smoke, which will show up in a bluish or cyan color, depending on how thick the smoke plume is. Of course, it does require people to identify red hotspots against a green background, so maybe not the best for people with color vision deficiency. And the utility of this RGB is quite dependent on how you scale the 3.9 micron component. And so here are 4 different versions of it, starting in the upper left with just linearly scaled radiance values, which does a pretty good job. But what I prefer is the solar reflectance calculation for the 3.9 micron band. It really makes these hot spots stand out as bright red, and has the advantage that there aren't very many surface features that are highly reflective at 3.9, so the fires really do stand out more. But unfortunately, the AWIP systems that the National Weather Service uses can only handle brightness temperature at the moment. And so the lower left is using the same scaling that we've applied to the Fire Temperature RGB. And the problem with this is that once you get to hot areas or arid areas, the background land surface is too red. And now you're trying to identify red hotspots against a red background. But if you bump up the higher end of the scale, even just by 10 Kelvin, you can do a much better job of suppressing that red background. And you get something that's pretty similar to the solar reflectance version. And here's an interesting example from last year using VIIRS, where the Jack fire initiated right on the edge of a previous year's burn scar from the Archie Creek fire. And you can see over the course of 2 weeks how this fire just burned right along the edge of the previous perimeter and didn't cross over into the old burn scar. Now, with my last few minutes, I want to talk a little bit about the value of true color imagery. You know, this is that special class of RGB where you take the red, green, and blue wavelength visible channels and make them the red, green, and blue components of the RGB. Because this product really is the best one out there for detecting smoke and other aerosols. And it also has the benefit that it's the most intuitive to people because it's designed to replicate how the human eye responds to color. But creating good true color imagery isn't as straightforward as it might seem. So here's an example from VIIRS looking at Korea using the red, green, and blue channels, where the raw reflectances are scaled linearly from 0 to 100%. And I think most people would look at this image and say that looks way too dark. You know, that's not what the Earth looks like when I look out the window. And that's because most land surfaces are poorly reflective in the visible channels. You know, there are software packages out there that will use a square root scaling by default, or you can think of this as a gamma value of 2 to bring, you know, to brighten up these dark surfaces. But even this looks a little muted compared to what we're used to. And that's because the human eye has more of a logarithmic type scaling approach. And so as I toggle back and forth, you can see how the logarithmic scaling does a better job of making those surface features pop out. But of course, the atmosphere looks hazy in this imagery because there's Rayleigh scattering going on in our atmosphere. But if you can correct for this Rayleigh scattering, now you get a clear view all the way down to the surface. And it really makes, you know, smoke and smog and other aerosol features pop out of the imagery. Now, when we first applied this to Himawari, we noticed that the Himawari true color, even when it was Rayleigh corrected, still didn't quite look right from what we're used to seeing from MODIS and VIIRS. And what we ended up finding out is that it's because the green band is offset. So the green band on Himawari is centered at 510 nanometers, which is offset from the peak in the the chlorophyll reflectance spectra, which is at 555 nanometers. And this is where MODIS and VIIRS are centered. So AHI is missing this vegetation signal and causing the true color imagery to appear too red or too brown. And it's also worth noting that the AMI on GeoComsat and FCI also have this 510 nanometer band. And so they are going to be missing this vegetation signal. And so our way of combating that is we've developed what we call a hybrid green approach, where we blend in a certain percentage of the vegetation sensitive channel with the native green band. And we have compared this against VIIRS. So here we're looking at an image of Southeast Asia from VIIRS, then the native true color from Himawari. And if we use 7% of this vegetation band and 93% of the native green, we get something that matches with what we see from VIIRS. And you can compare the results of our approach to other groups that have been working on true color. So the one on the left comes from KMA, and I'm not familiar with the details of how they produce this true color version, but just to note that there are different ways of doing this out there. And finally, I want to mention the geocolor imagery concept, since geocolor has been talked about quite a bit from the forecasters in the US. And the basic idea behind this approach is that we're blending layers of information together using opacity rules for higher up layers. And you can assign different colors to different layers. So for example, in this 2-layer example, we assign the top color to yellow, the bottom layer to blue, and then we apply this opacity to the top layer, and we can get a final product that varies from yellow to blue based on the opacity rules we've set up. And we can do this for each color component in the final imagery, and blend multiple different layers of information together into a single imagery product. And we can do this for as many layers as we want to. And so here's the basic idea how geocolor works, is that we start out with a base layer that has city lights at night. We do a low cloud detection algorithm that works at night as a second layer. The third layer is for high and cold clouds. And then the fourth layer is the true color imagery, which we get during the day. And then through this day-night blending factor, which is a function of the solar zenith angle, we can blend all of these different layers together into the final geocolor product. And one of the things that we are working on is integrating these Fire RGBs into this geocolor concept. So for example, you'd be able to see the fire information from the Fire Temperature RGB along with the smoke that you get from the true color component from geocolor. Or another thing you could do is blend the Fire Temperature RGB with our Proxy Viz product. So now you can see the fire at night, but you can also see the clouds, which you'd otherwise miss, once the sun sets. And so I will leave it here, and hopefully there's time for some questions.
Thanks, Curtis. So, Bodo, I see you have a comment. Would you like to verbalize that?
Yes, just bear with me for a minute. I've just temporarily been promoted to organizer, and my chat box is kind of, just bear with me. Okay, so I guess one of my comments, Curtis, is that in terms of this high resolution and greatly corrected RGB, a true color RGB. The Bureau have also developed a high-res version of that with 500-meter resolution based on AHI, and the forecasters really like that for detailed analysis. So that was one of my comments.
Yes, and I should add that our GeoColor product is running at 500-meter resolution over both the CONUS and the mesoscale sectors. So we have worked on that as well.
Yeah, and for those of you who use Slider, it varies. Some of the CONUS versions are 1 kilometer, some are. It's something we need to standardize. Bodo, did I cut you off? Did you have another comment?
No, that was it. Thank you very much.
All right, thanks.
Yeah, regarding this natural fire color RGB, I have a question. Why it's nice to have a smoke, and you said 0.6 is picking up this signal. Why not 0.5? Likely could better pick smoke. And why not on the green instead of 0.8 for the vegetation? Put 1.6, give you additional fire information and has some vegetation signal.
So but the second part first, I actually have not looked at the 1.6 and to see how well it would work for this RGB, but I have tested out this RGB with all 3 visible bands. So I've even looked at it from the blue, the green, and the red visible components, and it really didn't seem to make much difference.
Bernie?
I have a question because the small fires are also equally important in terms of detection. So, and I noticed that when we look at, say, fires over Central America or in Colombia, a lot of times we see them better with the straight 3.9 or the albedo product, you know, more of a reflectance type component that was talked about earlier. So do you have any comments on that?
I do think that the 3.9 albedo does do a better job of picking out fires, but for the fire temperature RGB, it seems to make the background land surface a lot darker than I think. You know, you'd lose some of this contrast between wooded areas and grassland areas that you can pick up.
Anybody else? All right, thanks, Curtis.